All right. You guys have been doing a really good job with the gas laws, and in the last couple of things that you've been learning a lot of different gas laws, such as these. P1 V1 over T1 equals P2 V2 over T2. You learned that this is Boyle's, Charles, and Gay-Lussac's laws all mixed into one, or this is what is called combined gas law. You also learned another law, PV equals nRT. I've been very impressed. You guys are doing a great job with your calculations and plugging numbers in and solving simple algebra. In a case like this, it's ratios that you cross multiply and solve. In a reaction like this one down here, you find the variable that you need and you solve for it. Now, at this point, we've learned gases, some properties of gases. Now, what we're going to do next is we're going to start applying it to reactions, because that's really the fun part of chemistry. What happens when something reacts and it's full of gases? And we've never done this before. So what you're going to find in this unit is we're going to take some skills that we've already learned and we're going to apply it to gases and the things that we've already learned. Let me give you one piece of information you'll need to know. Now, it gets really complex, but I'm going to give it to you in the easiest fashion that I know. And it works something like this. If you have a balloon and another balloon, let's assume those are the same size, and this one has hydrogen gas in it, and this one has oxygen gas. Now, so I have a balloon. Now, realize that these are diatomics. That's why they have the little 2's. If you have a gas at the same pressure and same temperature, you end up having the same number of molecules. Now, there's a whole lot of mathematics behind that, but basically what this says is you have equal amounts in each. Whatever the temperature, let's say it's at 20 degrees Celsius and a pressure of 1.6 atmospheres, you have the same pressure inside because of the same number of molecules that are bumping around inside the balloon. Well, they went a little further than that, and they actually found a little bit more detail than that. Now, as a matter of fact, let me say this. It doesn't matter what the gases are inside. It could be hydrogen and chlorine. It could be oxygen and nitrogen. It could be acetylene or propane or butane or whatever the gas may be. But if you have it at the same pressure, volume, and pressure, volume, and temperature, you have the same number of molecules bumping around inside. Now that's hard to show because you can't actually see the molecules, but they took that math a little further, and here's what they found. When you're dealing with gases, make sure you write this down. 1 mole of any gas, 1 mole of any gas at STP, now I'm going to come back and explain what that is in just a minute, is 22.4 liters. 22.4 liters. Now that's going to be very important. Now, a mole of any gas at STP is 22.4 liters. Now let me explain what STP stands for. STP stands for standard temperature and pressure. Standard temperature and pressure. There's your STP. A lot of times in books or problems you'll see STP and everybody's supposed to know what that is. So just to make sure we know what that is, scientists have decided what is standard temperature, what is standard pressure. Here it is. 1 atmosphere and 273 Kelvin. If you have a gas at STP, it's at this pressure and that temperature. Now, you also know that that's the same as 0 degrees Celsius. We said we can't calculate with Celsius. That's why I wrote it in Kelvin here. But that's what STP is. Okay, standard temperature and pressure. Make sure you get that down. Okay, so what does that mean? Well, here's what that means. If I had a mole of oxygen at STP, I have 22.4 liters. If I had a mole of nitrogen at STP, remember, STP is 1 atmosphere and 273 Kelvin, I have 22.4 liters. If I had a mole of butane at STP, I have 22.4 liters. It's sort of the magic number, 22.4 liters every single time. Okay, that's why it says a mole of any gas at, this is the magic part right here. If you're not an STP, then this is not true. Okay, If you're not at STP, then this is not true. But if you are at STP, it doesn't matter what gas you have. You always have that volume, 22.4 liters. So by definition, at STP, a mole of any gas is equal to that. All right, so make sure you get all that written down. If you have to pause the video, come back and pause that. I'll come back in just a second. All right, now what does this do for us? Well, let me go back to something you've already seen. Do you remember back in a unit before now, we talked about the mole, and we did things like this. We calculated from grams, and then we calculated to atoms and molecules. Okay, this is things we've done before. It looks sort of like a Mickey Mouse drawing type thing. And whenever you were at moles, it was always the magic number was a 1. Whenever you needed grams, that was always from the periodic table. You always got the grams from the periodic table. And whenever you had the word atom or molecule, you always use 6.02 times 10 to the 23rd every single time. Now, I told you in the lesson before now, we're not going to use this anymore, but I use this picture just to remind you. It's in your notes, just like this. Well, there's one part I hadn't shown you, and here's the part I hadn't shown you. 22.4 liters. Gases only. Gases only, STP. It's the only time it's true. So really this diagram, all of these things are equal to a mole. The weight off the periodic table is equal to a mole. So if I'm talking about salt, and I add them together, 23 and 35.5, that's 58.5 grams. You've done this many, many, many times. That's what I mean by using the periodic table. So if you need grams, it comes from the periodic table. You always get how much a mole equals by adding off the periodic table. If you wanted to count atoms and molecules, using Avogadro's number, 6.02 times 10 to the 23rd, always gets you back to moles. And we did those calculations. And again, we're not going to use these anymore. But it's the whole diagram all in one place. And then the third part that we hadn't talked about until this point right now is that a mole is also equal to 22.4 liters. Gases only at STP. Gases only at STP. It doesn't apply to anything else. So if you're dealing with a solid or liquid, this is not going to be true. Okay? Because it's gases. Now, why did I wait so long? Because you've just done a unit over gases and ideal gas law and all of these other things. This is the perfect time to show you how this fits in. So we're going to take these notes, and in the next video, we're going to start applying them. You're doing a great job. Keep up with me as we go along.